Hello everyone. Today we will be presenting our project titled Colorectal Cancer, a Dietary Analysis. My name is Landon Jones and alongside me is Emma Welsh. We examined how diet may influence colorectal cancer rates both in the United States and globally. We focused on identifying food patterns that may be associated with the rising colorectal cancer cases, especially among younger adults. Before we get started, on behalf of myself and Emma, we would like to thank the Symposium and Symposium organizers for the privilege of presenting today. Starting off, we would like to state that we have no conflicts of interest related to this project. Our analysis was conducted using publicly available health and nutrition data sources. Now, I want to start off by asking a quick question. By a quick show of hands, out of these four food groups, fruits, vegetables, red meats, and fats, which do you think causes colorectal cancer? Raise your hand for fruits. For vegetables, for red meats, and for fats. Well, actually at one point in time during our research, we had data that suggested all four of these were associated with high rates of CRC. A trend of colorectal cancer increases in younger populations within the United States, while rates have decreased in older populations as of 1999. The CRC rate used to be higher for the older population, which may have been in part by later screening times in life. But since the US started screening as early as 30, the CRC rates are still increasing in younger populations. It is likely this also reduced the rate in older populations. Our group decided to look at a few factors which may cause an increase in CRC in younger people. We looked at microplastics, pesticides, diets, obesity, and alcohol, and we narrowed it down to diets as being one of the most interesting and problematic causes of CRC. Internationally, our research concluded that one food group, meat, has the strongest association with CRC. Now, while population and dietary patterns are emphasized, they do not necessarily cause CRC. It is more likely that our population has other factors that assist in causing CRC, and it is not simply a single food. When looking at CRC incidence over time, responding to the consumption of one food group, we have a correlation coefficient value of 0.52, which indicates a moderate and positive relationship. We have a p-value of less than 1%, which means that our data did not happen by chance. We have an r-squared value of 0.989. This OLS regression is very high and not likely a coincidence. This means that it is a very good fit and shows that CRC is likely not by chance. An r-squared of 1 indicates a perfect fit where the independent variable explains 100% of the variance in the dependent variable. Now, we would like to mention that our research does need further individual consumption research in order to solidify our findings. Now, moving on to our hypothesis, the increase in colorectal cancer in men and women under 50 from 1999 to 2018 is partially due to poor diet. As we can see from the graphs, this is the trend of those younger and older than 50. We can clearly see a 41% increase in CRC since 1999 in the older population, while there is a 44% decrease since 1999 in the older population. Now, there are various materials we used in our research throughout our research. CDC Wonder is a wide-ranging data for epidemiological research. USDA/NHANES is essential data on nutrition, obesity, and diseases to guide health policy. Now, FAO is a United Nations agency that focuses on sustainable agriculture. Our World in Data is a free, nonprofit, scientific online publication that provides research and data to address the world's largest problems. IARC is the International Agency for Research for Cancer, and it promotes collaboration on research and identifies the causes of cancer and promotes preventative measures. Now, there were three main methods that we used for our research, being PCA, OLS regression, Bayesian regression, and Spearman time lag. And I'd like to spend just a few minutes going over each one because they help solidify our findings. Principal component analysis is the first, as well as OLS. Ordinary least squares estimates the relationship between one or more independent variables and a dependent variable. This occurs by using a linear relationship to express the data. Thus, it will show a linear relationship between the independent and dependent variable. Now, principal component analysis is highly useful when you have high-dimensional data with a large number of attributes, and you need to represent it with a low number of attributes. The general overview of this is that you have a three-dimensional cube, but the data itself is represented on a two-dimensional plane. What PCA does is it looks at the dimensions with the greatest variability. In this graph, you can see PC1 and PC2. PC1 will always be the direction of greatest variability, while PC2 will be the direction that is perpendicular to PC1. PC3 is very small and is sometimes used, and it points to the direction that is perpendicular to the hyperplane. Typically, you're going to pick PC1 and PC2 when you're doing principal component analysis. Now, the next regression type we used is a Bayesian regression. This relies heavily on Bayes' theorem. This is a mathematical formula that determines conditional probability. Conditional probability is the likelihood of an event based on prior conditions related to said event. When wanting to calculate the probability of a condition being true, let's say A, given that you know a condition B is true, this is when Bayes' theorem can be utilized. The probability of A given B equals the probability of B given A times the probability of A, all divided by the probability of B, is what Bayes' theorem states. Now, Bayesian statistics is all about updating beliefs. It is used to test a hypothesis, and based on that result, it will indicate how things work. Bayesian regression, instead of treating slope and intercept as fixed numbers, it treats them as distributions. Bayesian gives you a cloud of many possibilities. This cloud is a range in which potential outcomes may lie. These possibilities are known as the prior belief, and these can also be described as possible realities that may occur. Bayesian combines the prior with data, and the more data you have, the more certainty there is. This narrows down the cloud of possibilities and allows for a confident prediction telling you what data you can trust and what data you need to be cautious about. Now, the third and final method we used is the Spearman time lag. This assesses a monotonic relationship between variables, conversely to a Pearson correlation, which compares a linear relationship between variables. Spearman correlation works with the rank of data. You must first assign ranks of each variable, then take a Pearson correlation of the data. You do this by taking the covariance of the rankings, then dividing it by the standard deviation of the groups. In doing this, it shows when one variable is increasing, the other will also increase or decrease. But it is not necessarily a linear correlation. Instead, it is monotonic, which means that it is constantly moving in a given direction given the independent variable increases. Like I said earlier, these are extremely useful for non-linear relationships, and Spearman correlations are less susceptible to outliers as they work with ranks, making them extremely reliable if there is unusual or extreme data. Now, CRC incidence trend direction by age group. As we turn to this graph, the red indicates a positive association to CRC by age, and the green is indicating a negative association from 1999 to 2022. From this data, we can see that ages 10 to 14 get it the worst with an 11.38% increase in CRC rates, and ages 70 to 74 have shown an improvement or decrease of 3.68%.
Using the Spearman row by lag graph, we can clearly see which foods are correlated over 5, 10, 15, and 20 years. The deeper the red of the box, the more correlated it is to colorectal cancer. And the deeper the blue box is, the less correlation it has towards CRC. If you look at fruits, dairy, and grains, they do not correlate after 15 and 10 years. If you look at protein meats such as beef, veal, pork, lamb, and game, and starchy vegetables, they increasingly become strongly related over 20 years to CRC. And if you look closer at some of these values, not all of them make sense. Our group looked at this and we were puzzled. How does fruit, starchy vegetables, tomatoes, and grains cause CRC? Aren't those supposed to be cancer preventing? That made us think. We initially thought it was because most of our food is ultra processed or pre-made for us. We just weren't looking at it right. Our next few slides will help you understand our dilemma. At this time, we decided we needed to rule out a few factors. The Z-scores of obesity, plastics, which have a role in microplastics, alcohol, high fructose corn syrup, and PC1 are all put on a graph with CRC to show the trends from 1999 to 2022. But before I continue, PC1 is a diet made from foods on the previous slide that is based on our modern diet of America. PC1 includes positives such as cheese, oils, nuts, and poultry, and negatives such as potatoes, milk, starchy vegetables, and beef. The z-scores tell us how far something is from the average of 0. Since CRC rates decrease from 21 years from z-score 2 to -2, those that follow this trend are likely correlated with the rate. As we can see, PC1 and high fructose corn syrup also move in this trend. And obesity and alcohol and plastics follow this trend but in an opposite direction, showing that they are not associated with CRC. In this slide, we can rule out alcohol, obesity, and microplastic factors, while PC1 and high fructose corn syrup have an association to CRC. The OLS regression table compares the constant PCs and plastic Z value to the coefficient, standard deviation, T-stat, and p-values. We already know that PC1 is a modern diet, but PC2 is a much healthier diet that focuses on fruit, vegetables, little carbs, and proteins. And PC3 includes many types of fats that we do not necessarily relate to as Americans. If we take a look at our p-values, we can see that most of our p-values are at 0, which support our data. But PC2 has a p-value of 0.095. This value is above 0.05, which make our evidence for that one null. However, that does not matter as much as the R2 value, the adjacent R2 value, F statistic, and VIF. The R2 is very close to 1, which indicates that there is a near 100% correlation and that there is strong evidence associating these factors. They may be strong, but they are too high for our research. The adjacent R2 shows that we do not have too many predictors, and the F statistic shows that we have strong evidence. Then we take a look at the VIF, or variance inflation factors, which is over 100. This shows that there is something severely wrong with our data. Any VIF over 10 shows that there is severe multicollinearity. This means that all data is not reliable for interpretation. So we had to ask ourselves, how do we fix this issue? Our research group decided to focus globally to see what major factors could cause CRC mortality. Across 101 countries, meats, vegetable oils, sugars and sweeteners, and fruits and vegetables were at the top foods of this related to CRC mortality. If we take a closer look at the p-values, all but one are below 0.05. Fruits and vegetables have a p-value of 0.1848, which makes its Spearman data very weakly associated to CRC. Meanwhile, the Spearman of sugar and sweeteners and vegetable oils have a reliable and moderate correspondence to CRC mortality. Our meat has the highest Spearman of 0.516, making it our strongest correlation. Next, we compiled the data of several countries' dietary composition based on their food supply. Focusing on India, we notice that there is a significantly less food supply compared to all other countries listed. India has no poultry, which would be indicated in the lavender. There's approximately 20 kilograms per capita of sugars and sweeteners, located in the pink. Approximately 5 kilograms per capita of bovine meat, located in the mint green. And South Korea supplies nearly 30 kilograms per capita of poultry, 30 kilograms per capita of sugars and sweeteners, and about 60 kilograms per capita of bovine meat. Finally, the U.S. supplies approximately 50 kilograms per capita of poultry, about 60 kilograms per capita of sugars and sweeteners, and approximately 40 kilograms per capita of bovine meat. As we look at our partial correlations in total food supply, all but one p-value is below 0.05. Vegetable oils are above it, being 0.1143, which makes the partial p data not reliable. Partial p of this meat has the strongest association to CRC mortality. Sugars and sweeteners have a small correlation, while fruits and vegetables have a negative correlation, which actually helps fight against CRC deaths. We compiled a graph to show the global meat consumption compared to CRC mortality. The dots represent countries around the world, and the triangle is us, America. There's a shadow to show the general trend. It shows that as the meat supply increases, so does CRC death rate. In looking at our worldwide rising young onset CRC, we can see that all these countries have an increase every year in CRC rates. The largest value comes from South Korea with a 0.1625 increase, and the smallest value is from Denmark with a 0.0140 increase. The meat consumption versus CRC death rate Spearman row by lag shows that the darker the green, the more associated it is to CRC death, and the darker the red, the less associated it is to CRC death. Luxembourg has a trend from dark green to light green from 0 to 10 years before it transitions to white at 15 years or neutral CRC death rates. Brazil is consistently dark green, so the death rates have not changed over the years. Japan slowly changes from high to low death rates. And South Korea is consistently green. Kazakhstan was much better at 0 to 15 years before the 20th year, which has a large amount of death rates. We discovered that Kazakhstan has this trend due to poor diet change. We can also see that a trend from 0 to 5-year lags, there's an increase in deaths compared to the rest of the years. The left figure shows that total meat consumption in the 5-year lag has the strongest association to CRC death. And the right figure shows that the time lag of different meat subtypes. We can clearly see that the bovine and poultry meats are at the highest at 5 years compared to the rest, and pig meat is the lowest. Our research group initially believed we could find a correlation to CRC through poor eating habits. This was partially true. Everything seems to relate to CRC, but the strongest association is meat in younger populations. Our research group shows that more meat consumed by the younger population, the higher the CRC mortality rate, especially at the 5-year lag. We are not trying to say that meat is the causation of CRC, but rather a factor that may develop cancer over time.
For future research, in order to we could look at different things, including meat subtypes, different cooking methods, processed meats, or minerals/vitamins in meats. An example of this would be looking at meat subtypes and seeing how the various kinds could potentially cause cancer. These are some various resources that we used in our research.